guys know, it's our group project. In our group, we have Liu Zihao, Zheng Qingxin, and Lu Jingyu. And here are our metric numbers. In this video, I'm going to show the 3 simulation codes from our course. For each code, I'll explain the main purpose of each code and the function I have used and possible real-world applications and personal learning reflections after running the code. The 3 codes are MM1Q simulation with discrete event logic and exponential distribution simulation of bus waiting times. And the last one is MM1Q simulation with multiple load levels. The first code is MM1 queuing simulation. It's a basic MM1 queuing system using discrete event simulation. And the purpose of this code is to simulate customers arriving at a random times, joining a queue, and then served by a single server. The code tracks key performance metrics, including total number of customers served, average waiting time, and average queue length. So at the beginning, I have imported the basic libraries such as HepQ used to maintain an even list with the earliest event always processed first, and random to generate random arrival and service time with exponential distribution. And the last one is matplotlib, which can be used to virtualize the queue length later. Then I set the arrival rate and the service rate. The arrival rate is 10 packets per second and the service rate is 20 packets per second, and the total simulation time is 100 seconds. Once the time is equal to the simulation time, the simulation will stop. This setting creates a stable system because I think the service rate is higher than the arrival rate. And then I defined all the necessary variables here, and the event list, the queue, and the server status, and total waiting time, total number served. After that, I can use these numbers to calculate the performance like throughput or delay. Then defined the 2 functions, generate interarrival and generate service. One is to produce random arrival times following an exponential distribution, and another one is to produce random service times. This two reflects the real-world randomness in packet arrival and processing. Then it's the part of the arrival event schedules the next arrival and either start service immediately if the server is idle. But if the server is busy, it will queue the customer if the server is busy. And then it's about the departure event. This part handles a customer leaving the system. Either serves the next customer from the queue or makes the server idle if there is no one waiting. Then scale the first arrival event and run the whole loop, which continues until we reach the simulation time at the top. So finally, the code will print total served, average waiting time, and average queue length, and show a picture of queue length over time. Help me to virtualize the system congestion. Now I'll run the code. So here are the results: the total served, average waiting time, average queue length, and the picture of queue length over time to show the congestion. After running the code, On the X-rays, we have even steps, meaning each time either a customer arrives or depart, it will be counted as one event. And on the Y X-rays, we can see the queue length, which means how many people are waiting at each step. So, this picture matches our expectation because the service rate is 20, double the arrival rate 10. So the server process customers faster than they arrived and keeping the queue under control. So according to the results, this picture helped me to understand that in an MM1 system with light to moderate load, and the queue length stay under control, but there can be temporary spikes due to the randomness. And in this simulation, I used the basic MM1 queuing model to understand how random arrivals and service affect the queue length over time and come up with a congestion. And also this code helped me to answer the simple question like when customers arrive at random intervals and a single server processes them, and how often will the queue get long? The purpose of this part is to simulate the process, track the queue length, and finally virtualize the changes in the queue over time with the picture. And I have learned how to build a discrete event simulation using a priority queue and how to model random behavior using the exponential distribution like this, and how to virtualize the system behavior to better understand the queue dynamics with a matplotlib. The code helped me to understand that in network systems, if the server is fast enough, higher than the arrival rate, will sometimes experience short burst or congestion, but we can keep delays low and the queues may be short according to the situation. And in our real life, this means even a stable system will sometimes experience short bursts of congestion, but on average, the waiting time are manageable. Second part of the project is the exponential distribution for waiting time. This part focuses on the exponential distribution, which simulating the bus passenger waiting times. The purpose of this code is to understand how waiting times and random but statistically predictable when arrivals follow a Poisson process. I think in our daily life, the events like bus arrivals, packet transmissions, or customer arrivals often follow a Poisson process, and the waiting time between events follow an exponential distribution. And in the code, I first import the random to generate random waiting times and math to calculate exponential probability functions, and the matplotlib also used to virtualize the simulation results. First, I define the arrival rate set it to 0.1, which means on average, a bus comes every 10 minutes, and I simulate 10,000 passengers to get a statistically significant result. And the waiting time range is set up from 0 to 40 minutes to capture almost 98% of the waiting time cases. And then we can generate the random waiting time using the Python's exponential function and calculate the PDF and CDF curves using the exact formulas from probability theory like this. and pre-compute the mean and variance, which theoretically are 10 minutes and 100 minutes secured respectively. Finally, I use two figures. The first plot overlays the simulated waiting times with the theoretical PDF, and the second one is shows the CDF curve explaining how the probability accumulates over time. Now let me show the results. So in this picture, it shows the cumulative probability from 0 to 1. The red dashed line marks the mean waiting time of 10 minutes. From this curve, we can see that around 63% of passengers wait less than 10 minutes, and about 19 of passengers wait less than maybe 23 minutes, and probability approaches 1 near 40 minutes, meaning very long waits are rare, but also will happen in this situation. And this picture shows a PDF. On the X-rays, we have the waiting time from 0 to 40 minutes, and on the Y axis, it shows a probability density, meaning how likely a certain waiting time occurs. The light blue bars represent the simulated waiting time, and the blue line is the theoretical PDF curve. From this picture, I can see that most people wait less than 10 minutes, and there is a steep drop-off, meaning longer waits are less frequent. This picture closely follows the theoretical line and proving the simulation is valid. So according to these two pictures, help me to virtually understand why the exponential distribution has a long tail, which means that although most people wait less, maybe less than 10 minutes, but there's always a small chance of longer wait. So according to the second part of the code, I have learned how to use random generation techniques to simulate real-world waiting times like bus waiting time, and how to verify the accuracy of simulations by comparing theoretical curves with actual data like CDF and PDF. And I know the meaning of the CDF and PDF. It will show the distribution patterns and the practical understanding of mean and variance in a stochastic system. So the second project helped me to understand in transportation, networking, and queuing systems. Even if the average waiting time is fixed, but individual experience can vary greatly, and it is important to analyze both mean trends and extreme cases. The third simulation, I used an object-oriented approach to study how an MM1 queuing system behaves under different loads. The main objective is to observe both throughput and average delay to understand how the system performance changes as we increase the arrival rate closer to the service rate. And this reflects in real-world scenarios like computer servers handling more user requests and network routers dealing with increasing data packets or customer service desks under different rush hour loads. So I used a simulation class to structure the program cleanly, and it tracks queue status, counts of arrivals and departures, and also for the total waiting time. We simulate, and I also simulate 10 load levels from 1 to 9.5 with a service rate fixed at 10. And for each load, the simulation runs for 20,000 events to ensure the results are statistically reliable. And after each simulation run, we store two key metrics. The first is the throughput, calculated as departures divided by total simulation time. And the second is average delay, calculated as total waiting time divided by number of served customers. So here is the results. And finally, we also virtualize the throughput average delay with different loads. Now let's run the code. This picture shows the throughput with different loads. On the X-ray, we can have the arrival rate, which means load from about 1 to 9.5. And on the Y-axis, we can see the throughput, the number of jobs successfully served per unit time. According to this picture, the throughput increases almost linearly with load, and at a low load, maybe 1 to 5, the throughput is limited by the arrival rate because the server is underutilized. And as load increases up to 9.5, the throughput approaches the server's capacity near 10, which is the maximum possible throughput. So this matches queuing theory. The maximum throughput is bounded by the server's capacity, as we learned at the course. And the second picture shows the average delay with different loads. The X-ray again shows the different loads, while the Y-X-ray shows average waiting time, which means delay. And from the delays picture, when load is low, 1 to 5, the average delay remains very low and almost stable, meaning customers are served quickly. And from the load 7 to 9, we can see a clear upward curve, meaning the delay starts increasing as system load grows. So as the load 9.5, the average delay spikes sharply and almost doubling compared to load 9, meaning the system is nearing congestion collapse. So this picture is a key performance tipping point. When the load is close to service rate, the delays explode non-linearly, even though the throughput remains capped. So from this simulation, I have clearly understood the balance between the load and system performance. When the load is low, the throughput is low, but delay is minimal. And when the load is high, the throughput increases, but delay grows exponentially. The system capacity also limits the service rate. The throughput cannot increase beyond this no matter how much load increases after limitation. And I also learned the importance of operating below saturation in our daily life system to avoid long delays and ensure smooth service. So this exercise taught me how to use class-based simulation for cleaner code, and also learned how to virtualize performance bottlenecks using graphs, and interpret how system efficiency and user experience degrade near capacity limitations, and which is really important in the networking, cloud computing, and operations management and other areas. So as far as I'm concerned, from these three codes, I have gained hands-on experience in simulating the random process using Python and understanding the key concepts in queuing theory and probability. And I also know how to analyze the system performance using the real statistical output and how to virtualize simulation result for better interpretation. And uh, this course also helped me to improve my skills in discrete event simulation and performance virtualization. These things are really important and very practical and valuable for system analysis, network modeling, and optimization in my academic life. And thank you for watching.